So now what I want to focus on is if we were to view this molecule and try and come up with some kind of a coordinate system, I'm going to draw an eyeball right here, okay? And we're observing down the axis like this. So if I were to observe down the axis in this way, this is the picture I would see. I would see a spherically, assuming I can spell, symmetrical electron distribution. Okay, right, if I was looking down this axis. So basically if I took those pictures and I rotate them 90 degrees, right, so I'm looking right down the axis. And we're going to define this axis to be a special coordinate, and that's going to be the z dimension. Okay, so now when I look down this coordinate system right here, okay, x is going out here, y is going out here, and z is going in and out of the page. So we are going to define the internuclear axis. I'll try to draw it best I can, right? Z going, oh, I know what to do, right? I'll do that, that chemistry thing, right? You guys know what I'm talking about. Where I go like this, I'll go like Z and Z, assuming I did that correctly, right? So that's going to be special for not only valence bond theory, but also MO theory. We specifically define the internuclear axis, the region between the two protons, as the z-axis. And we're also going to come up with a new name for shared electron distribution that forms from constructive interference, and it's called a sigma bond if it's spherically symmetrical about the z-axis. Okay, so I didn't have enough information written there, but the sigma bond is specifically a spherically symmetrical shared electron distribution in the internuclear zone. Okay, that's important to note that distinction. Okay, moving along here. So let's do an example. So let's look at nitrogen. I'm going to put several examples together here, and I hope this is kind of familiar to you all from your Gen Chem and OChem and even inorganic chemistry days. So if we look at, we're going to use nitrogen as an example, but let's look at the nitrogen atomic electron configuration. Okay, that's 2s, oops, excuse me, that's a 1s2. So that's a 1s2, 2s2, 2p3, and of course we know from Hund's rules those electrons spread themselves out. And if we recognize here, we normally write that as 2p3, right? But really, I know that my p orbitals are comprised of px, py, pz. And because I have one electron in each, I'm going to have one electron in each, the px, the py, and the pz. Okay. We recall that a p orbital looks like this, right? Kind of like an 8 or something, right? That was a really terrible looking one. But we know that it's got the two lobes, right? The positive and negative lobes. If we were to look at this over a Cartesian coordinate system, assuming I can draw an origin, right? So that would be 0, okay? But now if we try to start combining these things, right? Because if I have one nitrogen and one nitrogen, that's going to make my nitrogen molecule. How do I form that first bond? Well, I've got these open p orbitals, and just like we in hydrogen, we took two s orbitals and got them very close together and got this shared electron density. We can now do the same, but with the nitrogen, we're going to do that with the p orbitals because our p orbitals are open, right? We only have one electron in each. And so now if I combine this p orbital and this p orbital, they pair up, and it still forms a sigma bond because if I were to look down this axis, I'm going to draw my eyeball again, right? if I were to look down that internuclear axis and rotate that 90 degrees, we would find this shape, as peculiar as it looks, it's spherically symmetrical about the z-axis. And so once again, my internuclear axis is the z-axis. So that means specifically these have to be pz orbitals. Okay? So one pz orbital and one pz orbital make my sigma bond for nitrogen. Lovely. So let's cross out those things as we're going. So I've used one of the pz1 electrons, and of course I've used another pz1 electron from a neighboring nitrogen molecule. So I'll just write that again so we know that we're doing two of them. 2s2, 2px1, 2py1, 2pz1. Clean that up a little bit. Okay, great. So I've used a 2pz1 and a 2pz1, and I formed one bond. But look, I've got 4 open electrons left, right? I've got a 2px1 and a 2py1 from each nitrogen. So how is that going to shake out? Well, remember, the px and the py are then going to be 90 degrees orthogonal to each other. So if we look at this figure now, and I'll remind you of our coordinate system, the way this picture is drawn, my z-axis is technically going this way, right? My z-axis is the internuclear zone. So there's a nuclei right there in the center, and there's a nuclei right there in the center. And so then, of course, I could call my x this dimension, and I could call my y this dimension. And so at this point, it doesn't matter which one is x and y. What's important to note is that z is the internuclear zone. So then now, here I've got my, I'm going to try to highlight this in a different color. So then this would be my px with the positive and negative region, right? And I'll highlight my px over here. Okay, great. And then now in, let's see, in a different color, in blue, I'm going to highlight my py. And so my py will span this way, which will be this guy right here, and then this one right here that's kind of hard to see that's back there. Okay? And then similarly, here is also my py right here, and then right here. Okay, so the red and the blue make up my py, and then you can even tell also in this picture, which I'm not going to highlight, my pz, right, the ones that form that internuclear sigma bond. Well, because there's open electrons in each of those orbitals, right, one in the px, one in the py, they can form a singlet pair across the axis, right, up here. So there we get another bond, which I'll indicate here, and we call that a pi bond. And by definition, a pi bond is off axis. It's not within the internuclear zone. And then, of course, we get another pi bond, 90 degrees to that out here, which I would draw right there. Okay? Fantastic. So I get triple bonds to nitrogen. And then, of course, we recognize that we have lone pairs on each, and those are going to come from the 2s shell, okay, to make those lone pairs. Lovely. So hopefully that's review for you, sigma bonds and pi bonds, but just remember, a sigma bond is in the z-axis, the internuclear zone. A pi bond can either be above that or out in front of that. And it's what we typically call the double bond. And of course, a triple bond is really 2 pi bonds and 1 sigma bond, right?